All right, so there's a couple of theorems that do come in handy for certain things later on down the line. And so let's go over, first one is, like I said, Rolle's theorem. It starts out, f is a function that satisfies three things. F is continuous on AB, f is differentiable on AB, and the only difference there is the including of the endpoints on the first one. And then also we've got f of A equals f of B. So we're focusing in on those endpoints there, A and B, and I'll draw the picture here. An example of what we're talking about, kind of get a feel for it, but those are the premises, if you will. And then the conclusion is, then there's a function, there is a number, C, in AB, such that f prime of C equals 0. All right, so yeah, these are our premises, and this is our conclusion for this particular theorem. Because sometimes it does ask you about those, so just understand, yeah, these three give us the conclusion there. We can go to our conclusion from those. All right, so here's kind of the picture of what's going on. I don't think it's too hard to understand why this works, because all right, so we've got a function, and we've got it such that it's continuous, which means there's no breaks. Differentiable, well, that adds to it, there's no corners, right? So it's got to be continuous and differentiable on basically the same interval from A to B. So here's A, here's B. And then we've also got f of A equals B. Well, that's telling me the function values are the same. And so if I start here at this value point at A, so my function value is here, whatever happens, the rest of the function, if f of A equals f of B, then it's got to come in at the same level there. A little better. Overshot it there. So you've got the same level there for f of A and f of B, if you will. Well, that's the premises. Now, the conclusion then says there's some C value in A to B, so some value out of this, such that the derivative equals 0. Well, the derivative equals 0 means what? Horizontal tangent. And so, yeah, we've clearly got horizontal tangent at, for mine, I'm going to say there. And so that's our C value that comes up in that conclusion. Okay? All right. So, there's a couple other cases, I guess, if you will. You could have, or just a couple others to consider. It could be that, all you have to do is finish up, if you've got f of A here, and then f of B is there, just as long as it's continuous and differentiable, there's all sorts of things that could happen. I mean, I could have it, right? I could have it go like that, right? Now, what does that mean? Well, that means there's two C values that satisfy this conclusion, isn't there? There's a horizontal tangent there, so the derivative is 0 there. At that C, call it C1. And then there's another one there, right there, call it C2. So both of those would satisfy our conclusion, right? The theorem just says there's at least one. There could be more, And in kind of an extreme case, we could have A to B, and then f of A, f of B. We could just go straight across there for my function. And so take your pick, right? Any of those would have the derivative, the C value anywhere, A to B, would be the derivative of 0 there. So that's pretty well what could happen in this scenario. But in all three cases that I put up here, and any other one that we could come up with, the same thing. We're still going to find at least one C value where you got a horizontal tangent, derivative is 0. Okay? All right. So what do they have you do here? Well, a couple things. They verify the function satisfies Rolle's theorem, the hypotheses or premises of Rolle's theorem. Then find C that satisfies the conclusion. And the function is f of x equals x squared minus 5x plus 3. We're going A to B is 0 to 5. So verify that the function satisfies the hypotheses or premises, called premises earlier. Same thing, hypotheses of Rolle's theorem. Then find C that satisfies the conclusion. Okay, so F continuous, we got to look at all three. So here's our verify. All right, number one, F continuous on AB. Well, is that the case? Is there anywhere, so again, think about continuity. Continuity just means there's no jumps or breaks. Well, does this function have any jumps or breaks whatsoever? No, it's just a polynomial function. It's continuous for all. So, yeah, that's true. Something like since f is continuous for all real numbers. It's certainly continuous on 0 to 5 because it's continuous for all real numbers, right? Number two, is f differentiable on AB? In this case, 0 to 5. Well, is there anywhere f is not differentiable? Remember, differentiable, the extra thing that could add, it's not differentiable where it's discontinuous, so if we had a discontinuity, that would show up in the first one, but what else could we have where f is not differentiable? At a corner, right? There's no corners in an x squared minus 5x plus 3 for any value there, so that's true again because f is differentiable everywhere for all real numbers. Ditto, right? Okay, now the third one is a little more maybe to show here. F of A equals f of B. Is that true? Well, in this case, A is 0, so the f of 0 equal f of 5. Let's just compute those out. What is f of 0? F of 0 would be 0 squared minus 5 times 0 plus 3, which is 3. F of 5, the other one would be 5 squared minus 5 times 5 plus 3, so that's 25 minus 25 plus 3, so that's also 3. So check, check. So, yeah. You're just thinking about those three. They just want you to think about those three. Okay? And the reason is, as you know, for this theorem to work, or any theorem to work, you've got to have all three, or all the hypotheses satisfied, or all the premises satisfied, before the conclusion kicks in. And that'll come up later on, so I wanted to mention that here. Yeah, if one of these three didn't work, we couldn't use this theorem. Okay, it's got to be all three, and then you can go to the conclusion. All right. So, what is the C that satisfies the conclusion? It's f prime of C equals 0. Well, how am I going to find that? Well, basically like we've been doing several times before, I'm going to get the derivative, which is 2x minus 5. Set that equal to 0, and solve that out. And hopefully we find one that works here. Let's see, so you add 5, and you divide by 2. So you got 5 halves. Now, the conclusion is there's a C in a B. Is that going to be the C there? Could we use that for C? I think so, yeah, because our A to B here is 0 to 5, and 5 halves, 2.5 is what's right smack dab in the middle of that, isn't it? So, yeah, so C that satisfies the conclusion would be 5 halves. Okay? All right. Now, another kind of problem they'll ask about, all right, so for f of x equals 1 over x squared, f of 2 equals f of negative 2. But for no c, but there is no c in negative 2 to 2, such that f prime of c equals 0. All right, so let's just explore that for just a little bit. All right, so for f of x equals 1 over x squared, we've got f of 2 equals f of negative 2. That's true. That would be 1/4. F of 2 would be 1/4. F of negative 2 would be 1/4. So the two function values there are equal. But there's no c in negative 2 to 2 such that f prime is, so there is no horizontal tangent in between there. I've got the two function values are equal, but there's no function value where you've got a horizontal tangent. Let's see, f prime of x would be, if I change that to bx to negative 2, easier derivative. The derivative is negative 2 x to negative 3, or negative 2 over x cubed. And yeah, if I try to set that equal to 0, there's no solution to that. Right? If I set that equal to 0, there's no solution. So there is no c. So why not? I thought this was a theorem. It works every time. That's the way theorems work. They work every time. Well, the answer is, back what I was saying here, the reason we were verifying that all three of these work is because for a theorem the conclusion to be true, all the premises have to be true. All the hypotheses have to be true. So is there one of those, I erased the theorem itself, but going off of this, yeah, I've got the third premise, right? But the question is, do I have all three premises? And which one would you say there? Well, I think we go either one of the first two. The first premise or hypothesis, let's say, so let's look at hypothesis 1 of Rolle's theorem. It's F is continuous on AB. Well, that was, in this case, F is continuous on -2 to 2. Is that true here? Is F continuous on -2 to 2? Where is F not continuous? It's not continuous there at 0, is it? Yeah, hypothesis 1 is not true. F is not continuous at 0, which is in -2 to 2. If we picked maybe some other, well, in this case we couldn't have picked, there's not another two values we could have picked to satisfy all three, but as far as continuity, if we picked something that wasn't including 0, that hypothesis would be okay. We'd probably run into some, with this one anyway, we'd run into some difficulty somewhere on the other hypothesis. But so this is so this is a good example of where for a theorem to be the conclusion to work, it has to be all hypotheses satisfied. If one of them or more, we could also use differentiable here, the same argument. If one of the hypotheses doesn't work, the conclusion is out the window there. You can't go with that conclusion. And here's a good example. Okay. So they'll ask you maybe a question or two in that sort of vein. Okay. Any questions on that? So yeah, that doesn't contradict the theorem. It's just because hypothesis 1 is not satisfied. Neither is hypothesis 2, but just one of them is all we need. Is that okay? All right.